Hey everybody, today we're going to be analyzing the structure of a wing of an aircraft. So as with my previous two videos, we're going to be recreating what you see on screen here throughout the course of the video. And so this is a wing for, a smaller aircraft like something like a Cessna or a Piper, kind of like general aviation. And you can see here if I turn off our contours and deflection, it has a full internal structure, and we're going to walk through how I created this, and recreate it step by step, and as well as the other, elements that go into a wing. So let me also turn on filled edges so you can see the mesh here. Before we begin, the programs that I'm using that you see right now is FEMAP with NX Nastran, and for CAD, I use Fusion 360. So Fusion 360 is just about the best program that you can get for free without, a subscription or, a large bill or whatever. It has a completely free license for hobbyists. I'll put a link to that in the description below if you want to follow along with CAD work. And then for FEMAP here, FEMAP is the pre and post processor. It's the program that you see up on screen, and NX Nastran is the solver. What essentially does the math to give us the stress answer. Both of these are pretty industry standard. They're used throughout the aerospace industry by a number of companies, and FEMAP with NX Nastran does have an educational license. So I will also put a link to that in the description below. So if you are interested in following along and creating this analysis yourself or something similar to it, you have those tools at your disposal. And then lastly, before we jump into the video, same as the last two, which were on space structures, I will be splitting this into 3 sections. The first one will be understanding the structure. We'll look at some diagrams and kind of get a sense for why why these elements look the way that they do. The second, we'll run through the CAD. I won't be recreating the CAD live, the 3D model, but I'll go through it step by step, essentially, and show each feature and what it does. And then finally, we're gonna start from scratch with a completely fresh file and recreate exactly what you see on screen here. So, you can see here the stress plot. This is von Mises stress. There's top and bottom von Mises stress here. So we'll jump into these stress plots and talk about what they mean and how to interpret them once we get to that section of the video in our recreation. But for now, let's hop over to the first section of the video. Okay, so understanding a wing structure. So I have some cutaway pictures here of wings, and you can see there's quite a bit of metal going on here. It's not entirely hollow, but hopefully when we're done with this discussion, this will all make a lot of sense. So let's start with going back to the theory, back to the basics. If you've taken a mechanics and materials class or strength of materials, any class where you analyze structures and calculate stress by hand, you of course are familiar with the concept of bending. But if you're not, that's okay. I have some quick pictures here that show, of course, bending is exactly what it sounds like. And in the case of a wing, you're applying an aerodynamic load, which creates a force upward on the wing, which hoists the entire airplane into the air, right? And that whole wing is in bending. So a wing structure is a very classic structure in bending, and it's sort of the job of the engineer to create a very lightweight structure that also maintains that aerodynamic shape needed for lift. So obviously, you could create a ridiculously stiff structure by making this solid metal, but then it's going to be so heavy the airplane's not going to lift off the ground. So we need to set up our structural element in such a way that it's as light as it can possibly be, it's manufacturable, and also it maintains this shape that we're looking for, this airfoil shape is what, let me draw. This is generally called an airfoil, that shape right there. So we want that shape to be maintained. So again, hopping back to the theory of bending, we have someone bending a ruler here. So what I want to discuss is the resistance to bending that something has, right? Because that's essentially what we need to design and analyze the structure's resistance to bending. The resistance to bending is the structure's stiffness, which often stiffness is represented by a moment of inertia. So you can see here Ix, and we'll talk about this a little bit more, but essentially moment of inertia is a property that depends on the geometry of the beam. And in short, you want to place as much material as far away from the bending axis that you can, right? So let's hop into that a little bit more. Imagine, you have this plastic ruler in your hand. So if you hold it like this person is, imagine you're holding this in your hands, you can bend this plastic ruler extremely easily, right? You can probably loop it back on itself. You can probably snap it in half if you really wanted. There's essentially almost no bending stiffness. But imagine if you rotate this 90 degrees. So now, instead of trying to bend it, in the direction that it's thin, imagine that you're trying to bend it, like this is the ruler, we have all of our measurements here. Imagine you're now trying to bend it like this, put your hands here and just try to bend it like that. It's going to be very, very difficult, right? You're probably not going to see any perceptible bending because it's going to be almost entirely stiff from your perspective to try to bend the ruler along the direction, that it is tall. So what exactly is going on there? Well, like I said, the moment of inertia, which is essentially the, resistance to bending, is dependent on your sectional properties. And essentially, if we are imagining this red rectangle here, let me change color since it's red. If we're imagining this red rectangle, imagine it coming out of the screen at you and it's bending downward. So it's coming out and bending down. B is the dimension that is, perpendicular to the direction that it's bending towards, and H is the dimension that the beam is bending in the same direction as. So you can see in this formula here we have BH cubed, right? Oops. So that we know that any dimension in the same direction that the beam is bending in is going to be cubed, whereas in the perpendicular direction, it's just B, just that number. So let's imagine the case where we have a ruler, and here's the axis it's bending around. Again, imagine it's coming out of the page. So that's scenario 1, and then this is scenario 2, and then this is the axis it's bending around, and it's coming out of the page bending downward, like, arced downward. So if this is, a 1/16 of an inch thick, and let's say 1 inch wide, we're going to do 1 inch wide, which is our B, times 1/16, and that's all going to be cubed. Let me fix that. That's all going to be cubed, right? So we're going to have some very small number, 1/16 cubed. And then we also have the 12, but we can omit that for now because we're just comparing the ratio. So 1/16 cubed is 16 times 16 times 16 is 1/4096, right? Now let's do the same thing. Let's just rotate a ruler. So now this dimension is 1 inch, and this is 1/16, right? So then the same formula. Now our B becomes 1/16, and our H becomes 1 inch. So 1 cubed is just 1, and then 1/16. So essentially, our ruler just rotated 90 degrees, trying to bend it in the direction of which it's most stiff, is going to be, and I think this is just going to be 256, yeah. So our ruler in the long direction bending is 256 times stiffer than our ruler in the bending it, as you see in the picture here. So, of course, that tells us a lot about designing stiff structures. You want to maximize your material in the direction that you're going to be bending. So, you'll see I-beams, like, beams that look like this. These are good at taking bending loads because they have, here's their bending axis, and then there's a lot of material far away from the bending axis, so they're very, very stiff, right? So hopefully that helped understand, what we need to make a stiff structure. And then, just for completeness, where is this I applied? So it's applied if you want to find the deflection of the beam. Deflection is going to depend on EI, E being the elastic modulus. But in our case, if we want to look at stress, is the moment, which is force times the distance, times C, which is essentially, this is the max stress. C is this dimension, the distance from the neutral axis to the top or bottom of the beam, divided by Ix. So you can see if we divide by Ix, the stress goes down when we increase our moment of inertia here, our I sub x. So that's kind of how it's applied. Okay, anyways, hopefully that tangent helps understand what we're working with here, because you can see here we have the shape of our wing, and our wing is, let me switch to a red, it's a bit easier to see, I think. Here's our wing. So we're trying to bend the wing upward, right? So like the wing wants to flex upward, like this, right? So we're bending the whole thing up. So ideally, we would actually want to orient the wing, 90 degrees around. So then we could have this like nice, like really tons of material here. And then like the wing would be super, super stiff in bending. The problem is, of course, you can't fly with the airplane's wings going into the airstream like a wall, because of course you wouldn't fly. So the aerodynamic engineers would tell us, hey, we need you to maintain this shape. And the structural engineers just have to say, okay, within reason, of course. They're not going to say like, hey, we need you to maintain the shape and it's going to be half an inch thin for 12 feet. But by and large, the aerodynamic aspect of the wing is going to drive, and the structural engineers have to figure out how to make that work. So let me erase some of these. So hopefully with that background, you can see the, design challenge that goes into a wing. But the good thing is humans have been building wings for something like, almost 100 years, actually more than 100 years. 2022, the first flight was in 1903. So wings also have been built before that as gliders. So well over 100 years, humans have been building wings. So, there are very well-defined structures that you can see right in front of you. So essentially, we have here our main structural elements called spars. That is this big blue beam that runs the entire length of the wing. And we have a front spar and we have a rear spar, this green one back here. These two spars are our sideways rulers, right? These are nice tall beams that are pretty difficult to bend along in the direction that we're going to be bending. So like essentially these blue beams run the whole length of the beam, and this is our tall ruler. That's very hard to bend. So that's the rear spar, this green guy, and the front spar, this blue guy. The front one is typically like the main structural member, just because it's in like the thickest part of the wing, so it's the tallest, so it's therefore going to be the stiffest. And typically, have your attachment points. It's going to take most of the load, and then the rear one is there to, help stiffen the rear part of the wing, and also sometimes, provide attachments and whatnot for the flaps and ailerons. So anyways, the skin, right, let's jump to that for a second, that you can see right here, that is responsible for maintaining the aerodynamic shape of the wing, right? If we didn't have any sort of skin covering, we would just have, you know, this skeleton moving through the air and nothing would happen again, because it's not an aerodynamic shape. You need that aerodynamic shape to turn the flow downward and therefore create lift. Now, the skin also in most modern aircraft and pretty much anything made of metal designed after like the 30s and 40s type of time frame, it's called a stress skin design. So the skin is not just there for aerodynamics, it is also part of the structure. That differs from something like airplanes with wooden wings with fabric over them. You know, the fabric is just purely aerodynamic, and the skeleton structure below takes all of the load. Whereas in you know, metal wings with stress skin designs, the skin itself is also part of the load and stiffens the entire structure. And you can see, you know, that also makes sense because if we're bending around, you know, like a neutral axis of our wing here, we can see that the skin itself is actually, you know, metal that is fairly far from the axis that we're bending around. So it does add some stiffness to the wing. So that's why our skin is kind of twofold. It provides the aerodynamic shape, and it also, in the case of stress skin wings, which we're going to be looking at today, it does stiffen the structure and take load. So our wing itself is very stiff now in the direction that we're going to be bending because of the front and rear spars, and the skin provides the aerodynamic shape and also stiffens the structure a little bit more. But keep in mind though that this skin is extremely thin, right? A lot of times on, you know, again, these smaller aircraft, the skin can be thinner than 1/16 of an inch. So like, you know, picture the thickness of that clear ruler that we're looking at, and it can be even thinner than that. Of course, it's made out of aluminum, so it's much stiffer already than a ruler, but it's on that order of magnitude of thickness. And you know, when you have just this shape unsupported, even out of a metal, if it's, you know, less than 1/16 of an inch, it's not going to be stiff at all. It's going to be very floppy, essentially. You know, it's not going to hold its shape. So we need essentially structural members along the length of the wing to make sure that the wing is holding its shape. And that's where these ribs come in right here. So they're aptly named because, you know, your ribs in your body descend down, you know, the length of your chest and provide protection for your, you know, vital internal organs inside your body, and you know, kind of give your chest area like the shape it has. Well, essentially that's what ribs on an aircraft do. The same thing. They give the skin here the shape it has. So the skin fastens all along the ribs to give it like a nice stiff shape, right? So now we have high stiffness in the length along the beam. Let me erase a bunch of this stuff because it's getting a little bit messy. So we have high stiffness from the spars in the length. We have good stiffness along the chord line. That's what the direction, you know, perpendicular to the spar is called the chord line. So we have good stiffness chord-wise that the skin sits atop, and the last structural element is the stringers. Right, so the skin will have aerodynamic pressures on it from you know, its flow, the flow moving around it. So essentially, if we draw like a skin panel here, this will have a pressure force on it. In the case of on top of the wing, the pressure is going to be up. Right, so it's essentially trying to pull the skin up. And so we have like all of this area through here is unsupported, and the pressure is pulling on it, or in the case of the bottom of the wing, it's pushing on it. Maybe that's a bit easier to imagine than pulling, is if, imagine you just put like a sandbag on the skin and it's pushing on it, And like we said, the skin is only a 1/16 of an inch, so it's not stiff when you're trying to bend it around its thin axis. So essentially, we want to add in some stiffening members called stringers between ribs here that also run along the length of the wing, the span of the wing. So we add these stringers here. So these orange members that run along the length of the wing. And then this gives stiffness to, the skin. So essentially we reduce the amount of unsupported area into compartments that are more manageable for the skin to retain its shape. Now I do want to show you, we turn on our deflected shape here. You can see essentially the skin. Let me turn up the deflections a little bit, do like 5 so you can really see it. Yeah, here we go. So you can see, here's a good example. You have our stringers right here, which are like these stiff beams, right? And then we have a pressure load on the bottom, which is trying to push that skin up, and is being, helped and constrained by the stiffness of these stringers. And you can see that along the length of the beam here. Do a little bit more so it's very obvious. Let's try that. Yeah, here we go. So you can see that the skin's making like a bubble kind of shape right here, and it's being held by, constrained and stiffened by the stringers. And same thing here to a much less extent because the stringer is far closer. There's a bubble shape forming. And then again, this is like the pressure or the suction side of the wing where you have pressure pulling it up, and you can see, we have between the ribs here, we have like the shape of the skin being pulled up. And again, it's held and constrained along the length by the ribs, spars, and these stringers. So hopefully that all makes sense. But, as always, please let me know if you have any confusion or if I didn't explain anything well. Always open to feedback and questions and discussions in the comments. But hopefully it's pretty obvious now what all these elements do, right? You have the blue and green spars, which provide stiffness along the length of the wing. You have the orange ribs here, which provide stiffness along the chord of the wing for the skin to retain its shape. And then we have these orange stringers, which provide local stiffness to the skin so it doesn't, lose its shape between all the ribs and the spars. So I also have another picture here. This one's pretty much the same thing. Yeah, not a ton different there. Again, we have spars and we have ribs. This one doesn't have stringers, which is why I switched to this one. Now I did want to show some examples of the structure on an aircraft. So I found a video of someone removing some parts on their, I think it's a Cessna wing rebuild. And he takes the panel off, and you can see inside the wing here. So you can see it's very, very thin sheet metal. So their airplane got damaged. And you can see here we have right here, let me zoom in a little bit. We have a stringer. This is a spar. You can see it runs between the two skins. Stringers here, we have some holes in them for lightweighting. Here you can see the damage, and you can see just how thin this metal is, right? You have very, very thin metal. This is probably damaged because of like a bird strike or something. This isn't like, everyday damage. This is like something hit the airplane while flying, or maybe on the ground or something, debris. But you can see how thin the metal is and how much weight they shave just to make these structures as efficient as physically possible. And you can see all the rivets or holes where the rivets go, because obviously they drilled them out to remove the panel here. And then there's a big skin panel here that's off. So you can see the internals of the wing. And I'll put a link to this video in the description if you want to check it out yourself. It's cool. And they do some like pan bys and whatnot of the wing. And then, we'll talk about this a little bit more. But I just grabbed this picture to show the flaps and the ailerons and like roughly, where they are on the wing. And then we'll talk about the pressure distribution once we get into the analysis. So I think that covers us for the structure. Like I said, let me know if there's any confusion or if I didn't explain anything well, or also definitely let me know if I over-explain things. If this is too obvious and I should just skip it and just give like a brief explanation, I'm also open to that. I want to make sure that the videos are accessible to anyone who is interested and wants to watch them and learn about aerospace structures. So let's now jump into the CAD model, which I have Fusion 360 for. So the airfoil shape, we're going to jump out of Fusion 360 in a second because this airfoil shape is not from Fusion. It's I downloaded it. There's a website that you can go to, which I'll link in the description, called airfoiltools.com, and you can essentially just like find airfoils that you want, and you can plot all the points of it and then bring that into your CAD program of choice to create a model of your airfoil. So I chose the NACA 2412, which is the airfoil of the Cessna 172, and this creates this will allow you to download a DAT file. So like these are all the points on the wing. This essentially is a wing that's it creates a wing that's 1 unit long, right? There's no units. This is just the raw points. And so what I did was, give me 1 second to open Excel. There we go. So what I did was I added a column of zeros because for Fusion to import a spline, you need XYZ data. So I just added a column of zeros. So to essentially, create the X data to put it all in one plane. And then I took that also data, and I took those points that range between 0 and 1, or actually -1 and 1. And I just multiplied them by 72 for 72 inches, which is 6 feet. So like, the width of the chord length of like a Cessna 72 is, roughly 6 feet. So multiplying it by 72 gets me inches. Now I did make a mistake. Oh yeah, and I saved this as a CSV. Now I did make a mistake. So I have my units in inches, and I imported our shape here, and it looks great, right? It looks like the shape of an airfoil. The problem is that this tool that Fusion 360 has, if we go to add-on script and add-ins, this is how I imported it. There is a script called import spline CSV, which you just hit the run button and you just select whatever CSV you want, and then it runs and it just plops you a sketch with all those points plotted out. The problem is even though my document is in inches, the script automatically just imports centimeters. So inches to centimeters is 2.54 centimeters in an inch. So essentially my wing was off in scale by 2.54 from what I expected. And I went through the entire design of the wing before realizing that I was not in the correct scale, and all my flanges and everything and where I planned to put my holes was all off. So essentially I had to go back to the beginning and restart. So just be warned if you're following along here, to import that CSV, go to scripts and add-ins, and then import spline CSV, and just remember that it is in centimeters, even if your document is in inches. Anyways, for this entire project, I used the surfacing toolbox. I didn't do any solid modeling. Let me jump back to the beginning. I'm using this bar on the bottom here to scrub through the features. So this is the feature directly from the import. I didn't actually touch that. And then I made another sketch here, which I'll show. So I converted that sketch and then just cut off the end. Right, you can see this amount of cutoff. Maybe I could have cut off a little bit more, but I essentially, if I jump back over here, I went with, you know, kind of like my best guess on like, hey, here's where the flaps and ailerons of the P-51 Mustang that we have right here, this is where they start. So like this is kind of where the main wing structure ends. Right along here, the main wing structure ends. So I'm just gonna, you know, cut off the airfoil shape right here and omit the flaps and ailerons in my analysis, since they're not going to significantly stiffen the wing structure, right? They're not vital to the structure of the wing since they move. And then I did a surface extrude. So just in the surface toolbox, just use the extrude feature. And then this is the scale feature. So you can see I just, sorry, that's the point. That's the point feature to create a point at the origin, so I could scale the wing from that. And then you can see I scaled the Z and the Y here by 2.54 to essentially get back from centimeters to inches here. So I did that like almost at the end of my CAD work and had to redo a lot of stuff. So if you're going to be recreating this and following along, definitely make sure that you set your scale properly. So keep jumping through here. So next feature, here are our two main spars. Let me hide the skin. So here are our spars. We have our front spar and our rear spar. I went with C channels here. There are different designs for spars. Some of them are C's, some of them are I-beams, some of them are like T stringers with panels connected to them. There's a lot of different spar designs. A C channel is definitely the easiest to manufacture, so that's what I went with, and to an extent easiest to analyze. Here are all of our stringers. So these are L stringers. So these would be fastened along the length of the wing on this surface, and then this surface that is, you know, perpendicular to it that extrudes out is for stiffness, right? And again, these are all just sketches. I could, oops, what did I do? Redefine sketch plane, no. Edit sketch. You can see these are all sketches, L's that sit along the offsets that I made actually. I should mention that really quick. So I made these sketches. So the material thicknesses that I decide, which we'll talk about more in the analysis, are, let me go over to my OneNote. They are, for the skin, I went with 0.051. For the spar, I went with 0.094. And for the ribs and stringers, I went with 0.063. So when you're setting up a surface model, you want your surfaces to be at the middle of the actual thickness of the material. So then when you thicken it, the program thickens it, all of your distances are set correctly. And I'll show you what that means in a few minutes if that doesn't make sense once we get over to the analysis. But essentially, this purple line right here, this is our skin mid-surface. So this first offset is for the ribs and spars. It's the distance of the skin, or sorry, the thickness of the skin plus the thickness of the ribs divided by 2 to, you know, get like the distance between the two middle surfaces. And then this is the same thing with the spars. So if we check out like our sketch here, this guy is on that line that is offset from the skin mid surface. Okay, let's keep moving here. So this is the ribs, or the first rib, I should say. So again, this is another offset and conversion of just the shape, like that shape that we imported. And then I added in some extra lines here that you can see that cut it at the spars. So, you know, this is a distinct surface. this is a distinct surface, and this is a distinct surface. So essentially we're cutting the ribs into 3 pieces so that the spar can be one continuous long piece, right? If we wanted the rib to be one big piece and the spar to be cut into different sections, then all of that bending load of the wing would have to go through fasteners, whereas when we cut cut the rib instead of the spar is just one long piece that runs along the length of the wing, which is what we want. Here I made some circular cylinders essentially around the rib to stringer interface, and then just use the trim feature to edit here. Use the trim feature to essentially cut out what's inside that cylinder. So then we just create like a clearance from the rib to the stringer, because the ribs and the stringers don't need to be attached to each other. So, that allows the stringers to also run the length of the wing. Moving forward here, these are, again, similar idea, just creating some cylinders to create holes in the rib for lightweighting. So again, exact same thing here, all the same features, just removing some material to make the rib much lighter. Okay, here I am creating the flange. Obviously, we need to be able to bolt the ribs to our skin here, and we need to be able to bolt the ribs to our spars. So these are flanges. Of course, these would be bent on a machine, like a forming machine, that will, it uses like a tool and a die to press the sheet metal into the shape. So these extrudes are just essentially, I use this tool right here. Where is it? Create, and then project/include, and then project, and then you just select the edges that you want, and that creates that edge in the sketch that you can use to extrude. These features are to stitch those new extrude surfaces together, because before, just when you extrude, they're not combined into one solid surface. They're all separate surfaces. So the stitch feature, if I do edit here, you can see it just connects them all together basically. These are fillets or radii, so obviously you can't bend any sort of metal at a completely sharp angle. It's always going to have a radius, especially to the mid surface. So this adds radii to everything. Let me jump a few features ahead. So you can see we have a radius on the spar, we have a radius on the ribs, and a radius on the stringers on all the edges. And generally for aluminum, it varies on alloy and temper and whatnot, but generally for aluminum, if you can be like between 1 and 2 times the thickness is your bend radius, then you'll be in good shape. So you don't want it to be so crazy tight, because then you can get cracking and whatnot, and also generally you might have a bit higher stress with very tight radii. So if you can be a little bit generous with the radii, you'll be in good shape. So that's adding radii to all these edges, so these transitions are nice and smooth. And now I think I start essentially doing a ton of split face operations. So let's see, that's just the plane. Here we go, you can see them. So we'll talk about this a bit more when we jump into the FEM in a few minutes. FEM means finite element model. But essentially we want to create something that allows us to connect the structure together easily with elements that represent fasteners. So what we're doing here is just creating some lines. And you can see those lines correspond on the ribs and on the stringers. So we want to create geometry ourselves so that we can add lines so we can reference those lines. So if I jump ahead, we added a ton of planes, which I'll show all around. We have planes that are on our stringers. We have planes on our spars here. And then a bunch of split faces. You can see now we have nice intersection points that we can place fasteners. And then we're going to use a lot of pattern features and whatnot. If I hide this guy again. So this is the model. And you'll notice it's quite short. That is because in the case of this wing, some wings do vary along their length. In fact, like, you know, most commercial airliners that you see and fly on, they'll have wings that taper down, and probably they're swept back a little bit. So they're not going to be like these big, long, straight sections, but a lot of times wings for smaller vehicles, like the Cessna 172, which actually, let me grab a picture of it. Like this style plane, you can see that the wings are, you know, fairly like straight across and the same section all the way down. There might be a little bit of difference here and there. See if we can find a top view. That's a tiny picture. So this one looks pretty straight. I think there's a good one. So you can see there is a little bit of taper back, but you know, by and large, we're straight for like this section, and we're just slightly tapered on this section. So you know, to reduce the time to completion, I just went with a wing that's you know, straight and the same all the way along its length. You could apply pretty much all of these properties or all these methods that I'm using if you wanted to analyze a wing that was different along its length. It's just going to be, you know, a little bit more time consuming to set that up. But, you know, for now, I'm just using a wing that is can be patterned. You know, I'm going to do 4 patterns of this kind of compartment. Okay, so once you're ready, you can do File, Export, and then you can change it to a step file, STP, STEP, right? And then that'll save all of these surface bodies. And now let's go over to FEMAP. We'll do File, New, and we're going to go File, Import, Geometry. And you can see there's a bunch of different versions here because I think V15 is when I realized I had the wrong scale and exported and got into FEMAP and was like, why is my wing so short? And then I think these are a few different minor iterations that I went through just to make sure that all the geometry was set up properly. But anyways, we're going to go with V26. Okay, so now this is actually important. When you get step read options, these settings you can leave fine. What you definitely want to uncheck those optimize bodies. Essentially, FEMAP will read the surface bodies, and it'll all those nice lines that we made, like the split bodies or the split faces. It'll essentially remove them because it'll see they're not required geometry and be like, oh, these are edges that I don't need, and just remove them. So make sure you uncheck optimize bodies, otherwise you're going to import something and it's going to be missing all of your model prep that you did. So we hit OK, and there we go. Now we have our wing in FEMAP. And you can see we have all of the lines that we set up here. If I hop back into Fusion real quick, I did make one on just like the very front here, to just make sure that we're splitting up the wing in a way that's makes sense. So I'm going to call this first layer geometry, or just geom. And I'm going to create a few new layers. I'm going to call this guy skin upper, and create a third layer and call it skin lower. So we're going to leave most of the geometry in the geometry layer. So essentially layers allow you to turn off and on different aspects of your finite element model. So if I turn off the geometry layer here, obviously everything we have is in the geometry layer, so it disappears. If I turn off these skins, nothing happens because we just created those. So we're going to go with modify up here, layer, surface, and then if you hit right click and then do pick front, it'll pick what your cursor is over and not like the normal or like the center or what it's centered around. So essentially what we want to do is just select all of our upper surfaces here. Hit this little highlight button to make sure we have our upper surfaces selected. We do. Hit OK, and then change this to skin upper. And now what that allows us to do is turn off our upper skin, right? So now we can essentially see through the model, but also leave on our lower skin, which will help us tremendously when we're setting up the model. And now we also want to go with modify layer curve. We want to make sure all of our curves that go along with the upper skin here are in the right layer. And then we're going to go with method on surface. And we're just going to select all these surfaces. There we go. Hit OK and move that to skin upper. And we can turn off our skin, and points we're just going to leave because I'm not going to really use any of the points in this video. Now we just want to do the exact same thing for the lower. Okay, just finishing up now. I probably cut that out a little bit so you can see less clicks, but hit OK and skin lower. Okay, so now we have a geometry layer which contains all of our spars, ribs, and our stringers. We have a skin upper layer, which we have the top side of the skin, and we have the skin lower layer. So now we have everything nice and organized. You can also export separate bodies if you want, and then drop them into different layers. But I think this is easiest, especially because the skin upper and the skin lower are still one connected surface, except we just have the actual surfaces themselves in different layers. Okay, so now we want to go ahead and start creating our mesh here. So let's start by creating our property cards for the different elements. So we're just going to start with making one for a material card for aluminum. So this will just be like the actual aluminum material properties. Now we only need to run the finite element model, we only need Young's modulus, which is 10,000 KSI. So 10 with 3 zeros is 10,000, and then KSI to PSI, 3 more zeros. And then Poisson's ratio for aluminum is about 0.33. And that's actually all we need to run the finite element model. If you don't input a shear modulus, FEMAP will just calculate it based on Young's modulus and Poisson's ratio. We're not applying any thermal loads, so we don't need to worry about this stuff. We are going to be looking at stresses, but we can just look at the output of stress. This is if you want to output like a margin, essentially have the program do that, but I prefer to do it myself. And then we can add a mass density if we want. We're not going to be doing an acceleration in this finite element model. Perhaps we will with this model in the future if we revisit it. And then if you have transient analysis and want damping, you can add that in, but it's not necessary. So there's our aluminum property. Okay, now we want to use this property. So we're going to be doing a plate mesh, which is essentially you give it 2D surface geometry, which you can see is all we have right here. And with that 2D surface geometry, you have different properties that inside the card there's a thickness associated with it. So then you essentially generate something that approximates 3D geometry with 2D elements. And generally 2D elements are just as accurate as 3-dimensional elements, like like the tetrahedron elements that you'd be seeing if you just hit mesh on like a basic analysis program. But the main benefit is you can get the same accuracy with way less elements. On something like this thin-walled wing, it's going to be like an order of magnitude difference meshing it with a solid tetrahedron elements versus 2D plate elements. So where you can, definitely use 2D plate elements, and they're very, very common in industry. A lot of times spacecraft are analyzed with nothing but 2D elements, and there actually aren't any 3D elements at all in a finite element model. So, you're not cheaping out and going with a less common solution by using 2D. It's actually quite the opposite. 2D is more common than 3D elements. So we're going to add in our materials here. So we have Let me jump over to OneNote so I can remember here. So 0.094, 0.063, and 0.051. So we want 0.094 thick, and then just where it says thickness, 0.094. And you can see we selected aluminum 2024. Hit OK. Let's make another one. Aluminum 2024, 0.063 thick, and oops, input 0.063. And then the last one was AL 2024, 0.51 thick. Okay, great. So now we have our 3 property cards with our different types of aluminum. So now let's hop into meshing. So the meshing itself of like the skin and the surface and most of the elements is going to be fairly straightforward. We'll do a little bit of playing with it here and there to make sure we get a decent quality mesh. But by and large, we've already blocked out a lot of the stuff that we need to. So it should go pretty fast here. So I jumped over to the meshing toolbox down here. So for starters, make sure you change property to whatever you want to be using. In this case, aluminum 2024. Actually, let's do the skin first. And let's just try to match the colors here. So I did blue, purple, and green. Let's hop back over to, so the skin will leave as blue. This guy will be purple. And then we'll make this guy green. Let's do like that. Okay, we can always change that later. Hop back over to meshing. So we have our skin thickness selected, 0.051 inches thick. We're going to turn on mapped meshing, which just means it tries to make a constant grid, which is what we want. Then we're going to set the mesh size to 1 inch. And press this select button up here. And we can start meshing. And you can see we've generated a mesh on the surface. We want to go with color width, property colors, and hit F6 to bring up the view options, and go to tools and view style, fill edges, and change that to use view color. So it just becomes black lines instead of lime green. And then let's also, while we're here, let's do background solid, and then let's just give ourselves a white background instead of the gradient blue. Okay, now let's continue meshing. So essentially we're just going to, am I in the wrong layer? I am in the wrong layer. I'm going to do this once per video, I think. So essentially, layers are buckets to put parts of your finite element model in. And whatever layer that you have selected, so you can say I have geometry selected because it's a blue color, is going to be the layer that the element is placed in, or whatever you create is placed in. So I want to select skin, but my elements that I just created are still in the geometry. So I'm going to go to model layer, modify layer, mesh, and then we can just hit shift, select all this, hit OK, and then change that to skin upper. And now you can see the geometry layer no longer controls the presence of these elements. So now let's continue on. So we're going to keep meshing here. Just want to click on the surfaces, the smaller surface as well. And now you can see, because we have that line here, now we know we have a node, which is just the corner of an element at the locations where we need them. Okay, so now here we could use 1 inch elements, but let me just turn off surfaces. You can see it kind of around the nose tip here where we have high curvature. You can see, here's where the elements are supposed to be following, and just because they're square elements, they kind of cut the corner and they don't super closely follow the geometry that they should. So we're actually going to increase this density a little bit. And if we go to increase, so now essentially we have 4 elements here, 1, 2, 3, 4. So let's just do set 2 and let's double it to 8. So if we hit this guy, now you can see it's still not entirely perfect. You know, if we wanted something really, really close, we would have to use many more elements. Like if we used, say, 32, then you can see it's much, much better, but we simply don't need that mesh density. So we're going to leave it at 8, which is kind of good middle ground. You can see the mesh is definitely more dense down here, and it follows the contours of the geometry much better. So we're going to go back to mesh surface. Now we're going to go to our lower skin, turn back on our surfaces, and just keep going with the mesh here. So we'll modify that sizing in a second. Let's just get through all the skin. There we go. And now we're going to go back to mesh sizing. Set 2 still on, and then 8. And there we go. So if we turn off our surfaces and our curves, we now have a mesh of the contour of the skin. Okay, let's not waste any time here and just get right into the spars. So we're going to create a new layer called spars. Hit OK. Make sure it's active, and then we'll turn back on our surfaces and we'll turn off our skin. Go back to the meshing toolbox. We're going to go to mesh surface, and now we're going to change it to our 0.094. And we can go ahead and mesh our spar. Like so. There we go. And then the other one. So you can see because we did all that geometry and prep work, the model is coming together pretty quickly. Where is today? Maybe you guys saw that, but I could have swore I did activate the lower skin, but I told you I would mess this up multiple times for video. That's okay. Let's go to modify layer, mesh. Okay, there we go, and skin lower. There we go. Okay, now you can see we can show our skin elements, our lower skin elements, and the spars, or the upper skin elements and the spars. Okay, so there are our spars all modeled up. Let's make a new layer, call it our stringers, and let us just keep going here. So we're going to go with our 0.063, and let's just turn off the top and bottom skins. A bit easier to see. There we go. Now I think we want to add, yeah, let's add a second element. We'll do that in just a second. Okay, so now what we want to do is, we do want to have, 2 elements here, just to make sure we're getting the density that we need. So let's increase by 1, and press this edge, and it adds a second. What happened to this guy? Looks like it's missing one of its surfaces, 2 of its surfaces. There we go. Okay, go back to mesh sizing. Oh, I did it there too. Okay, and there are our stringers done. So you can see we're kind of getting somewhere. The last thing to mesh is going to be the ribs. Let's turn our surfaces back on and let's just jump in. So we're going to start with 0.5 mesh size now. And see how that looks. I think that's what I went with on the other one, so we're going to stick with that, and then we're going to increase the number of elements on either side of this split line here. Turn off our lower skin. Okay. Looks good. Let's keep going here. Okay, let's do the radii now. We'll have to fix that in a second. Let's actually just go ahead and mesh everything. Okay, now let's turn off our surfaces for now. So I don't know why it does this, but sometimes when you have a map mesh and you mesh another component, it just tries to like decrease the number of elements. So we're going to go to mesh sizing, increase, leave it at 1, and we get that square surface once again. Did it do that on the bottom too? It did. So like I said, let's increase our element count along this edge. Looks like that did it. This guy. There we go. Sometimes you just gotta play with it. I don't know why it was trying to reduce the element count along that edge, but you know, if sometimes you just use the mesh sizing toolbox and increase and decrease it, and you can kind of get it to fix itself usually. So keep adding our additional elements so we get more mesh density around our flanges here. What has happened here? Let's see. That's a bit better. Okay. So triangles, you generally want to avoid triangular elements. You want to avoid they are not as accurate as four-sided elements, but a few here and there are going to be okay. The thing to just look out for is if your highest stress is, you know, a triangular element, it's the results can be a bit questionable. So, oh, I realized I forgot to do the flanges to adapt to our spars. Turn on the geometry for that, and we'll looks good. I think I might have changed something there. We'll have to fix that. Not a big deal though. Okay, and I think we got them all. Okay, so let's go back to mesh sizing. This, for some reason, has done this triangular collapse. Let's just increase it. This one has not. That looks okay. Over here, let's add some more elements. Actually, if we want to, we can turn off of our spars and stringers and our geometry. So now we can just see our ribs here, or our rib, I should say. Okay. So let's see if we can make some of this geometry look a little bit better. So let's increase density here. Okay, well, it's not perfect, and there's still a decent amount of triangular elements here and there, but I think I'm going to call it there. There are a bunch of techniques which perhaps I'll do a video on in the future about how to, get spend a bit of extra time and get a really great mesh for fairly complex geometry, and a lot of times it comes down to, before you're even in FEMAP, kind of masking out your surfaces and trying to essentially guide the elements into uniform shapes. Perhaps I'll do a video in the future about that, but I think for our purposes here, this is okay. And if you're just doing something quick and dirty in industry, or even just like a stiffness model, kind of like what we're doing right here, where you're not going to be pulling stresses from it, this would work. There are plenty of places that would be totally fine to pull stresses from. There are just some areas that, wouldn't be super great, like back here, this element in this area is not going to be super accurate. There's a triangular element there. There's a few others. Like things like this aren't going to be super great, but again, they're not going to be that bad. So I think you'll still be within the right ballpark. Here's another triangular element right here, like that might not have the best stress output results, but by and large, it's good enough, and it'll be certainly stiffness accurate, and the stress will be mostly accurate, except in like a few problematic areas. And if you encounter those areas in your mesh as like the high points in stress, then you can always remesh and rerun to make sure that you're getting the accuracy that you need. But this isn't too terrible. It's workable. So let's continue on here. You can now see we have our mesh all ready to go. So the next step is to, of course, start connecting everything together. So let's start with our easiest connectors. We'll make a new layer, call this span-wise connectors. Span-wise meaning along the span of the wing. So, in this view from left to right, that's span-wise. Let's turn off our ribs for now. And essentially, we just want to create a connection between our stringers and our skin, as well as our spars in our skin. So how do we do that? I'm going to use a spring damper element to represent a fastener. So let's call this a generic fastener. So there are a couple different ways to calculate stiffness of a fastened joint. Like in this case, it'll be rivets. In other cases, it'll be like bolted joints with a screw and a nut, or a screw and a threaded hole. So there are a few different ways to calculate that. For now, I'm just going to leave them as approximate values of what they would be. So let's do. So you can see here, essentially the way this works is, this is our degrees of freedom. So this is a 6 degree of freedom spring, which means it has a stiffness in all 6 directions. So 3 translations and 3 rotations. And these values are the stiffness. So this is these first three, 1, 2, 3, these are the translational stiffnesses. 1 is along the axis of the bolt, and then 2 and 3 are the the two lateral directions. Then 4 is the twisting of the spring around its axis, and then 5 and 6 are the bending of the spring. And these are all values that you can calculate a stiffness for. So we hit OK. Now we can model all of these joints as springs. So we're going to go to Model, change our property to generic fastener. Oh, I think it's a feature of FEMAP actually. When you just create a property and you go to Model Element, the type automatically selects the property that you just made. But if it didn't, if it said like, something else like plate or whatever, then we could just go into type and hit spring damper. So orientation, we want to select a node, and basically what this does is allows us to define the Y direction. So most of the time with fasten joints, you have your stiffness in the lateral directions is the same. So like essentially your direction 1, your DOF 1 is stiffness along the length of your bolt, and then the other two are in perpendicular axes in the lateral direction. So it doesn't actually matter where you select the node for the orientation. Essentially you're selecting, hey, this node, create a vector that points from my spring element to whatever node I'm going to select, and use that as the direction 2. But since 2 and 3 are the same, we can essentially select any node we want. And if it's the node doesn't have to be like planar with the lateral axis of the bolt or spring. Essentially it'll just like snap the vector to that plane. So basically what I'm saying is for a bolted joint that has lateral stiffness the same in all directions, you can just select whatever node you want as long as it's not on the axis of the bolt. So we're just going to select that one. And let's go ahead and start modeling. We're in the right, yep, span-wise connectors. Actually, I think it might be easier to do it like this. So we're going to select our 2 nodes here, hit OK, and there's our first connector. So let's just do that for all of these. Okay. 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 That's all of them along the bottom. Let's turn on the upper skin and turn the wing upside down here. Hit OK. Okay, so now we have the starting blocks of all of our span-wise connectors. Now, of course, we want these connectors to extend down the length of the wing. So how do we accomplish that? Well, it's actually quite easy. So first of all, we want to start by measuring the length of our elements, distance between nodes. So we set it to 1 inch, but sometime, if the program, it doesn't have an even increment of 1 inch between elements, which in this case, I don't think it does, because I think I set this distance to 0.75 and the total wing length is 48 inches. So it's going to have like 47.25 inches to play with. It'll just default to like a multiple. So yeah, you can see it's 1.005 between elements. So just copy this number. And now we're going to want to go to mesh copy element. And let's select all of these springs we just made. And hit OK. Okay, and now we want move along vectors. Good. Geometry we don't want to bring. I don't think we would bring any geometry, but just in case. Numbering default is fine. Same properties, leave that on. Then we're going to change the approach to pattern. Hit OK, and now it says define our pattern. So number and pattern, we're going to do, I think 11. Now let's pull up our calculator. And we're going to do times 4. So we're going to put our fasteners 4 inches apart. And we'll get this number and input that. And then our pattern alignment, we're just going to do it down the x-axis. And did I do enough? I think I missed. I think we actually want 12 to get us to the end of the wing or close to it. So let's go mesh, copy element. Do this again real quick. Hit OK. And pattern, yes, all the settings are the same. And this time let's just change it to 12. There we go, that's much better. Yeah, and then there's one right here. And then when we pattern the entire wing, there'll be one right here, which is perfect. Okay. Now, we have just patterned these connectors down, but they're actually not connected to anything. We just patterned the element and it brought its nodes with it. And you can see, I'll prove that to you. If we, like this is one of the first ones in the pattern. Let's change our selection to be element. Edit this guy. You can see the nodes selecting are 4672 and 40672 and 40666. And these do not have anything that starts with 40. So if they don't share a node, they're not connected. Very easy fix for that, since we pattern them to be, exactly on the nodes. All we have to do is go to turn on the whole mesh, go to tools, check coincident nodes, select the entire thing, hit OK, and we'll change this to something very small because we know they're very close, like 0.002. Hit OK, and in the bottom you can see it says 220 nodes merged. So now all of our nodes are in fact connected up. Okay, so we're getting there. We now want to do our rib connectors. This is a little bit more involved. We potentially could have prepared this ahead of time with geometry, but I think getting the planes oriented normal to the skin would have been tricky. So I think this method is probably, just as valid. However, if we wanted to, so essentially what we're going to do is determine the position of fasteners based on the mesh. If we want to determine the position of fasteners in our model and then mesh that, then we would have to put some sort of feature or cut in the surface to tell the program like, hey, I want a node here, so I can, add a connector, and then it'll do that. Also, one thing I generally do, if I have holes in my model, I'll fill those holes with a surface but leave the outline of the hole, and then you can add a node to the center of that surface and then remove the surface using FEMAP. I'm sure I'll do that in the future in some other video. So we have to do this across the whole rib. I'm just going to do it on like this one section, and then I'll skip ahead and have the other ones done, because I don't think you guys need to watch me do every single click here. Turn off our spars and stringers. Did I? No, okay, good. So essentially what we want to do is let's also turn off our ribs and just turn on the geometry layer. So what we want to do is just pick some locations for our connectors to go. So on a real wing, you can often see like there's hundreds of fasteners connecting the ribs. There's hundreds of rivets connecting the ribs and the ribs and the skin. I'm not going to model all of those. I'll just model them, at a few inches apart. to get the right idea. So what we're going to go to is model node, and we're going to go with method on node. Now we just want to node ID. We just want to select where we want a fastener to be. So we'll do here. Move down a little bit. Maybe here. Down a little bit more. Here. A little bit more. Here. And here. Okay, so now we've created some new nodes on top of other nodes. So if we turn on our nodes display here, you won't be able to see them. But if we go to modify, where is it? Project node. And now we see we can the dialog here said node 1 through 5 created. So we're going to go 1, 2, 5, then hit the more button. Now you can see we've selected the nodes, hit OK, and then project onto surfaces, direction closest normal. Hit OK, and then the surface that we want to project onto is this guy. And then OK again, and now you can see it has brought these nodes up. And if we turn on our ribs now, we now have these nodes on our surface. So let's go to model, element, type. We're going to go to rigid, go to RBE3, which says interpolation. This is an interpolation element, so it connects nodes without stiffening them. So essentially it interpolates the stiffness of the central node based on the stiffness of the independent nodes. So the dependent, which is like what inherits the stiffness of the nodes around it, is going to be this guy, and our independent is going to be, we turn off rotational control on RBE3s, the 6 nodes around it. Then hit OK, and let's change this guy to pink. Okay, now you can see we've essentially connected this node to the 6 nodes around it with no stiffening whatsoever to the mesh. So we just need to do this on all of these nodes here. Okay. Then this guy. So in some cases you can just do like merge nodes, like the coincident nodes check. I like to stick to an approach, but it would also be totally valid to just merge these 2 nodes. You know, make this guy come to the one we created. But I'll stick to the same approach. Okay, now you can see we have 5 nodes on this surface. And now essentially we have what we had before, where we can just go to model, element, type, spring damper, change our property to generic fastener, put our node somewhere out here, right? And now we can we have 2 nodes right on top of each other. And then we can just go through and add in all of our springs here. And now if we turn off the ribs, you can see now we have a connection made between that rib section and the skin. And we'll have to do this on all of these sections as well as the spar connections here. So I'll go ahead and do this real quick and then get back to the video. I'm going to do exactly what I did here, which, just to walk through the process again, I create new nodes on top of nodes on the skin that I want to use for fastener locations. I go to modify project and then node to project them onto the surface. Then I connect them to surrounding elements on the rib with RBE3s, and then I connect the central node with the skin, and now we're all hooked up. So I'll be back in just a second after I finish connecting all these. Oh, and real quick, I just wanted to mention that you don't need to do, each surface individually. You can project like a number of surfaces, because it just, the node will go to the closest one. So you can see I have a bunch of nodes selected, and I'm just going to select all of the rib flanges here, and it'll bring up a bunch of the nodes all at once, like that. So you don't need to have, you don't need to do each surface individually. Okay guys, we are all connected up, and this is a completely connected section of wing that we are ready to pattern. But we don't actually want to pattern just yet, because if we made a mistake here, or something isn't connected properly, or there's any sort of error or issue with this model, and then we pattern it a bunch of times, we'd have to fix it the number of times we patterned. So what we're actually going to do is run a quick analysis on just this small section, to essentially apply some load and make sure everything runs properly. We get results, we get the deflected shape looks good and everything. So let's create a new layer for our ground connectors. So we're going to do a very, very simplistic ground connection for now. In the future, I'll probably do another video on a spar connection to the airframe. I think that would be a cool way to revisit this model and expand it. But for now, we're going to do a very simple connection. So we're going to do a new node at center, and then we're going to select all of our nodes along the spar, just like this, and then hit OK. And then we're going to want to do the same thing on this guy. So method on curve, select all the curves, and then hit OK. So I'll talk about this a bit more when we look at the stress results, but generally when you're looking at like a spar connection, and I have a picture of one that I'll show shortly, but when we're looking at a spar connection, it's like a very beefy bit of metal with some nice big holes to put bolts through and whatnot. Definitely the one of the more beefy parts of the entire airplane. And for now, we're just going to omit that. But I think we can definitely revisit this in a future video and design some nice spar root reinforcements. But yeah, for now, we're just going to leave it as is, and we're going to use some RBE3s and springs to connect it to ground. And you'll see when we look at the results of the finite element model, there's going to be very, very high stresses right around the root here, because in reality the root will be a much thicker material. So we're just going to use our nodes here, move those away from the rigid here, and then do model element, spring, and we can actually leave this on orientation to the coordinate system, since these are perfectly aligned. Okay, so these are our ground connectors. Obviously this isn't quite correct, and you'll see there's very high stresses at the root of the wing, but I think we'll revisit that in a future video. So let's go to our constraints. We're going to go new. We're going to call this fixed wing root. Hit OK, and then we'll go to constraint definitions, nodal, and let's just constrain those fasteners, those springs, and then we hit fixed. So now we have constraints, and now let's create some quick loads. So we'll create a pressure load when we do the whole wing, but for now let's just do wing test load, and we'll go to nodal. Let's select a few areas. Let's do, how about one on the skin here, one on this bar, one on this bar. Let's do one on the upper skin, and I think that'll do. Okay, and then let's just apply, we'll apply 200 pounds in Z, so it'll be 800 pounds total. And we'll apply 50 pounds in Y. Okay, now we have some forces. The skin's going to be massively overstressed, but that's okay. We just want to make sure everything's connected and working properly. I'm going to go manage. We're going to go with new. Call this wing test load. Hit next. This content you can leave unchanged. These are some settings, like if you're doing acceleration, sometimes you want to check weight mass. These are a few other settings like large angle, large displacement, if your stiffness changes drastically based on the deflected shape. But in general, the defaults it goes to work. You can do geometry checks. I'm going to leave this off for now. I went over geometry checks in, I think, my last video very briefly. And then model check, just make sure everything's constrained to ground. Usually this will output in the file, so you can just check it. So if you have any issues, you can, reference this, and sometimes at some companies even make it a requirement for you to report to your weight and ground checks. Master constraints and conditions, I don't like using these. I just prefer to leave these at none. And then our outputs, we want displacement, applied load, constraint, force, that's good. Then force, stress, and I also like to put on our strains, even if we don't use them. So analysis case, we're going to call this fixed wing root dash wing test load. Hit next, and now our constraints are going to be fixed wing root, and our loads are going to be wing test load. And hit OK. Now, if we've done everything right, let's save and analyze. See what we get. And there we go. You can see it was extremely fast. It's only 12,000 elements, and it took 4 seconds. 4 seconds to run, and only 0.4 seconds on the actual system. So that's good. And let's turn on. So we'll start with our total translation. Okay, you can see we're massively deflecting the skin, but that's okay. You can see the stringer is coming along for the ride, which is good. Everything's all connected up here. I'm just looking for any areas that, so it defaults to percent of model. We're going to change this to actual deformations, which is even more because, you know, our skin is not designed to take a 200-pound point load. But again, that's okay. We're not paying attention to what this load looks like. We're just literally just doing a quick test load to make sure everything's all connected up. And it looks good. I don't see anything that seems to be flying off into space incorrectly. Obviously, this guy's penetrating through here, but that's okay. If you want to really, really eliminate any of that, you can use contacts, but that's going to greatly increase the complexity and runtime of your model, and generally it's just not needed. So yeah, you can see here our stringers are deflecting down and the skin's getting pulled back up into the ribs, so everything seems to be good. Now let's check the stresses. They're going to be ridiculous on the skin because of those point loads. Let's see, we want plate top von Mises. Now let's set this up. So data conversion, no average centroid only is what I generally do, and then turn off continuous colors, and then hit this and go to no magenta. And you can see, let me change it to max threshold. Oops, and then let's do 30,000. I think that's a reasonable number for aluminum 2024. And yeah, obviously the skin is being greatly overstressed, but everything else seems not too bad. Okay, so I think we're all connected up properly. Just for let's do edit where applied, and let's go ahead and delete our two. Did I delete the right ones? I did not. Let's do edit where applied again, delete these two, and then let's just select our spars. Okay, and then let's do edit load. And let's bump up this to like 500. So now we can see something that looks a little bit more realistic instead of this absolutely ridiculous shape. Okay, FEMAP thinks we're almost out of memory, which is not true. And so now you can see this is significantly more realistic, but you can still see, like I said before, at the wing root is, you know, has the most stress by far. And that's where you would have very thick material. And we'll talk about that in a bit. Okay, so everything looks like it's acting correctly. Turn on maybe a little bit too much. Here we go. Here's 30 times displacement. And what's going on here? Okay, I think that's just the bending of the C channel. 10x looks a little unrealistic, but you know, again, if we put it back to 1x, it's fine. And everything looks good. So we are ready to pattern this mesh. So let's turn off our ground connectors. And then we're just going to pattern this thing. So let's go mesh, copy, element. Let's select everything we got here. Then we'll hit OK. So we want move along vector, yes. Other entities to include. Now we do want to include geometry, and we don't want to include loads or constraints. So we want to bring the geometry along with it now because we want those surfaces to apply pressure to. Numbering default is fine, same properties, yes. And then we're going to do pattern. Hit OK. And then our wing is 48 inches long right now. Number and pattern, we're actually going to do 5. We only want 4 of the box sections, but we want a rib at the end. So we're going to do 5 and then delete the rest of the elements. Now hit OK, and there we go. As you can see, that was pretty easy. And now let's go ahead and come over here. And we'll go to delete model mesh. and just try to select as uniformly as possible. Make sure everything looks good. It does. Then hit OK. Okay, delete unused properties. I always hit no, but there won't be any unused properties. And now you can see, I think we probably wanted to do one more element in, but that's okay. Let's just leave it. So now we have our wing. But if you remember last time, when we pattern something, it doesn't connect it automatically. So we're going to do the exact same thing. And we'll go to Tools, check, Coincident Nodes, select all of these. We'll change it to something like 0.003, hit OK, and then it says 828 nodes merged, which is good. Okay, so now we have our much longer wing. We still have our ground connection at the root here. And let's now create a pressure load. So this will be, like I said, I'm going to do, probably going to do a future video revisiting this finite element model. The other thing I want to do in that video, the first one being the ring root, is take a look at data surfaces to get us a nice pressure distribution. So if I scroll down here, this is what a pressure distribution on a wing looks like. So below the wing, you have the pressure side, where you have positive pressure that pushes the wing up, and then on the top you have the suction side, which is negative pressure, which also pulls the wing up. So basically, this is how the wing is loaded. This like pressure applied to the surface. So we want to approximate this in the model. Now we can approximate this kind of curve around the wing, but it's a little bit involved for this video, since we've already created the model and the mesh. I thought I would keep it a little bit more simplistic as far as pressure, and then we can revisit creating something that looks just like this in the future. So basically what I've done here is 19,000 square inches. That's our surface area of the wing, top and bottom. So if you just do like 48 times 4 times, I think 60, which is the chord length, you'll get this number. And then 2,400, that is the approximate weight of like a smaller aircraft. So we're just going to assume that weight is held up by just this one side of the wing, which is probably a good approximation, because when you hit turbulence and whatnot, it is going to increase the force on the wing. So anyways, that's the approximate weight of the aircraft. And then if we take 2,400 pounds divided by 19,000 square inches, we get 0.1263 psi. Right, so this is approximately how much pressure would be on the surface if it was uniform to generate 2,400 pounds of lift. So we're going to also vaguely approximate this curve. We're going to put, I think it's 0.125 on the front section, and then we're going to put 0.075 on the rear section. And then that'll get us like roughly 2,000-ish pounds, which is what we want. And like I said, in a future video, we'll revisit this to generate a more accurate pressure curve. Okay, so let's turn off everything except our upper skin for now. And let's also turn on our surfaces for the skin. So let us go to our loads. We're going to do new, and we'll just call this wing pressure load. Right, and then we'll go to load definitions, and now we actually want to do on surface this time. Select our surfaces. So I think we'll do something like that will probably work. And hit OK. Now we want a pressure. It's already selected. And then direction, normal, element, face. That's correct. And then we're going to do let's do 0.13. Hit OK, and then turn on view loads. Okay, now you can see the pressure is in the wrong direction. This is the suction side of the wing, so we want to actually reverse this. So we're going to go to edit load, and then we'll just change the symbol to be negative. And now you can see we're doing it, we're applying the pressure correctly. And then we'll do another load on surface, do the same thing here. Actually, yeah, I'll remove these surfaces in just a second. But there we go. And we'll call this 0.06, which will give us about 2,000 pounds of lift. It should, hopefully. And then, oh, I almost forgot. We want this to be negative. There we go. So now we have 0.13 in the front and 0.06 near the back. And then let me do edit where applied and change this to remove. Select all these guys. Oh, I think I missed some. Okay. Let's do the same thing for the bottom. We're going to go to load definitions, on surface, select surfaces. Let's do these guys. Hit OK. And we're going to change this pressure to 0.13. Hit OK again. And then that's already in the correct direction. And then we'll do one more. We're going to do a on surface. Let's straighten it out a little bit more. And then perfect. And then again, 0.06. Okay, now we have our pressure loads. Again, a rough approximation of the pressure on a wing. Let's turn off our loads so we don't have to look at that anymore. Turn off our surfaces. And then we can turn back on. Let's leave the upper skin off. Hit save. Okay, we're almost ready to see our final results here. We're going to just go ahead and copy the wing test load. And actually all the parameters we can leave the same. We're just going to go into our boundary conditions in case one. Actually, let me save it first. We'll call this fixed wing route and then wing pressure load. Put that in the label too. And then we want wing, instead of wing test load, we want wing pressure load. And oops, I didn't rename this. Okay, now let's just hit analyze, and it'll be a little bit slower, but probably still less than 5 or 10 seconds. Let's see. It was 19 seconds. So twice what I said, but still 19 seconds isn't too bad to wait. So let's start out by looking at our, so I'm going to turn off our spring elements here so we can just see the mesh. So just turn off our connector layers. And let's go to wing pressure load and look at the deform shape. And you can see we are, as expected, turn on some animations here so we can see it. I like to do, oh, we can leave it on full apps or just full frames. Let's do maybe 32 frames. And the delay will change to 30. And then we actually just do full apps. So this is just like the load pushing it up. And that looks pretty reasonable. Turn on the upper skin here, see how that looks. Looks good. Let's change the deform to like 10. Set that the fixed, and you can see it looks just like the other one where we have on the bottom the skin's being pushed up, and on the top it's getting pulled up. And again, it's getting pinched down around the ribs. So this all looks good. Let's now check out our von Mises stress. So we have it set to 30,000 here. The skin looks good. You know, if we wanted to, we could potentially even go thinner. You know, in reality, this would be a couple panels, different panel sizes and whatnot. We've just modeled it as one big skin, which is, you know, not a terrible approximation. You know, it'll be a little bit of extra stiffness, but not terribly wrong. But, you know, we'll have different panel sizes, so we could probably even go a little bit thinner down here. Just so we can see it a little bit better, let's drop it down to like 10,000 PSI. And now you can see, again, let's do 8,000. So you can see we have high stresses where the skin's being pinched. We have high stresses where it's being pushed in the center. So along the ribs, along the spars, along the stringers. This all looks correct as it should. Same thing on the top here. And we can actually turn off our filled edges so we can see a little bit easier. So again, this looks like what we expect. And as we get closer to the root of the wing, again, as you expect for a cantilever beam, the stresses get higher and higher until right at the root, we have some very, very high stresses. Set this to 14,000, and I will turn off our upper skin. So again, you're looking at our spar here. We have very, very little stress. You know, all the way at the tip, we have almost no stress, just a little bit from, you know, the connection to the rib. But as you go along the length of the beam, you increase stress. So, you know, here's like an increase again, and then as we get towards the root here, we get very, very high stresses. So let's set this a little bit higher so we can see what's going on here. 50,000. I want to say that the strength of 2024 is something around like 50 or 60,000. The ultimate strength, I can't remember exactly. So you can see in general, you know, the beam is okay, except right where we have it connected, and we have some crazy, crazy stresses here, which, oh, what happened? I don't know. The model went flying away there. And you can see, we can see in the bottom corner, yeah, we have like 160,000 PSI on this element right here, which is just ridiculous. So same thing over here, probably we have, yeah, 130,000 PSI. 160,000 PSI is like the strength of, you know, like 8286 aerospace bolts. And you're certainly not going to make your wing spars out of that type of material. And like Inconel, like nickel super alloys can withstand those type of stresses, but certainly no aluminum can. So that brings me to the other point I've been alluding at. So, you know, you can see here in this picture, you can see like how thin, you know, our ribs are, and you can see our skin and whatnot. Like that is as we've modeled it. But then right where the wing ends, or sorry, the root of the wing, right where the wing ends, we have this like crazy thick material. You know, something like, it's like 3/8 of an inch or 1/2 an inch or something like that. And we have multiple plates. We have like this L here sandwiching this T with that thick material, and another one here. We have, you know, another plate here. It's connected up to straight through to the rib. We have these big bolt holes that mount the structure. We have these big ones on top, which again will mount the wing root. So like the moral of the story of this picture here is, right, we have a ton of material. Like we're still modeling 0.091, where this is more like 3/8 or half an inch, like 3 or 4 times what we have, and it's like a fairly integrated structure into the geometry of the spar here. So this phenomenon that we're seeing, which actually I don't think I've done this before on this model, if we turn on thickness, we can see we have this very, very thin root, and we're getting very high stresses, and that's, we would expect that because if we look at other designs of wing roots, other engineers encounter and are aware of the very high stresses at the root of the wing, so they make very, very beefy, nice structures to withstand those stresses. So I think, I'll probably revisit this model in a future video, and we'll design something that looks fairly similar to this, so we can, get like essentially a model that has stresses that work for the material that we're using at the root of the wing. So yeah, and you can see, that this thin material works everywhere else except the root of the wing. Like if we put this back to 30,000, you can see again, the ribs look good. Like everything looks good. It passes the stress criteria. It's just the wing roots here are way overstressed. So that'll definitely be a future video where we'll revisit this model and design some nice beefy wing roots. But otherwise, let's turn off the lower skin here. Turn off our spars. You can see some high stresses in here. This element might not be super great, but otherwise a lot of these elements look good. Some high stresses here, but by and large the ribs look good. And again, we have high stresses right near the root. If we look, something a bit further away, we're totally fine. Stringers are also good. They're, stiffening elements can be a bit deceptive, even though they have very low stresses, and you might want to thin them out. As you thin, your stiffening elements, they take less load and, are worse at the job of stiffening the shape of your wing. So even though it looks like maybe we could thin these guys out a ton, you don't want to do it too much because then it loses the benefit it has on stiffening your structure. Although, that being said, most of the stiffness comes from the bent flange here, not necessarily from the thickness of the material, because remember our discussion before about the ruler, like thinning out this material is going to be much less significant to the total stiffness of the stringer versus making the stringer taller. So you can play with a lot of parameters, and at the end of the day, you have like a single finite element model for your entire wing. So you can change your geometry and find and arrive at something that works. Oh, and I almost forgot. Let's go ahead and check the force on the springs at the root of our wings to make sure we got our pressures right. It's always good to check whatever you can. So we're going to go to list, output, results to data table. And then we can do element and, oops, did I click on the wrong thing? List, output, result. I think I might have hit result to ranking. It should be results to data table because that menu didn't look familiar. You can change how the table is going to be organized, but for now we can just leave it like this. And then we want to select fixed wing root, wing pressure load. Check our bush XYZ force. Bush is like the spring. C bush is the nastran, like name of the element. And then we'll select our two springs here. Oops. Hit OK. And then it outputs, so we can see we have, if we take a look at our Z force, which is the force, you can see the Z axis here, that's the direction of our wing, and we have negative 250 on the rear one, and negative 1750 on the front one, and stemming that gives us 2,000 pounds. So we were more or less on the money as far as getting like roughly 2,000 pounds of lift on this wing. So the cool thing about these data tables is, let me just show you guys real quick. I'm going to turn on all of these connectors, turn off the ground connectors, then we'll go to model, and we'll go to turn off plates and rigids. Now you can see we have a ridiculous amount of fasteners. And we go to list, output, results to data table, output sets, in columns, we want to leave that, output vectors in columns, we want to leave that, and then nodes/elements in rows, and then I do alternate column order. So we get like all the X forces, all the Y forces, all the Z forces. And then we want to do our wing root. And remember, these ones we use a node to orient them, so they're not oriented to the global coordinates. So it'll be X is the axial force and Y and Z are the lateral forces. So let's hit OK. And now we select all of our elements, and you can see we get a massive table of every single element we have on here. And then you can see here's our forces. So we have X is our axial force and Y and Z are our shear forces. And when you have a lot of cases, you can export this data to Excel by clicking this copy clipboard button, and then do any sort of data transformations or max mins, whatever you want. But there is some data down here that automatically does that for us. So it looks like our max X is 130 pounds, which is reasonable. Our max Y is 3,440 pounds, which is pretty crazy. If these were rivets, they're probably going to be like 800 or 1,000 pounds. So we definitely have a few rivets here which are being very overstressed, and those are most likely going to be at the wing root ones. Like if you look at these values in the Y column, we're looking at like some of them are like almost 0, some of them are 1, some of them are like 200-300 pounds, which is reasonable. 60 pounds, 80 pounds. Here's 50, 200 again, 400. A lot of these are very reasonable values, probably far away from the wing root, and that's probably just the wing root that you have. Again, those ridiculous 130 KSI stresses that would go away when you quickly design a wing root. Also, are going to generate extremely high fastener forces. I'm just scrolling through to see if I can find it here. Of course, if I brought this into Excel, I could find it very easily, but oh, actually, duh. It says max ID is 41956. Let's find that. 956 is right here. Yep, there's 3,544 pounds of shear. So let's just highlight that guy. Let's do model or modify edit element, and then we're going to go to 41956, hit more, and yep, it's at the root right here, as expected. Again, it's the one right on the spar at the root, which of course has a ridiculous amount of load on it because there's a ridiculous amount of stress in the root, and we haven't designed that proper beefy nice big bolt hole spar root connection that I was showing before. So by and large, though, the rest of these fastener forces look as we expect them, and good to go. So let me put our model back to how we had it before, like that, and we'll close the data table. But anyways, that's how you analyze fastener forces. So I think that's just about it for this video. Like I said, in the future, we'll revisit this finite element model, and we'll do like a proper pressure curve on the surface using a data surface in FEMAP, and we'll design ourselves a wing root that looks a whole heck of a lot better than this. But hopefully this video was still useful and informative to see the process of making a much more complex finite element model than just like a single part, and how to connect things together. And like I said, this is you know, a wing that is the same section all the way down. If you were to, you know, if you wanted to analyze a wing that, like, say, tapered backwards, or it got smaller at the tip, or, you know, like the majority of wings do, your techniques are going to be all exactly the same, right? You're really not going to do anything different. The only difference is, you know, we saved ourselves a lot of work by just analyzing one section and then patterning all the way down. If you can't do that, then, you know, you just have to go section by section and mesh the whole wing, which can be very time consuming, but the techniques and everything are all the same. So if you wanted to do that, you certainly could. But, you know, just for time constraints and everything, you know, this works in getting us a pretty good looking finite element model. And, you know, hopefully we can learn something along the way. So I don't think the revisiting of this finite element model will be the next video. It'll probably be a few videos down the line, you know, just because I like to mix things in and do different structures and whatnot. But this video will definitely come in the future, so look forward to that. And let me know what you guys thought of the model. You know, was everything clear? Everything makes sense? Let me know. Maybe I did something wrong too. That's entirely possible. So as always, feel free to give me any feedback or ask any questions in the comments. And I'll see everyone for the next video. Thanks.